how machine learning works. First, before I show the script, like how to use the scikit-learn package, I would like to briefly explain machine learning. So this graph shows basically what machine learning is. The thing is, um, let's see, I have some images for dogs and I have some image for cat. I just gave all the images to the model. The model learning is like it learns the patterns within these things. And it's basically just a function try to figure out how to do prediction for these model images. After that, once that's trained, we call this process training. Once it's trained, we can give new data image to the model, and the model can tell us what it is. It's a dog or it is a cat. So it's just a pattern recognition. This image in this example, we usually call it instance or like a sample example. And based on how the data is given to the model, there's a supervised learning and unsupervised learning. And supervised learning is just all the data is labeled. I mean, label, which means like, for example, an image, I will tell the model like this is a dog. I could also say this is an animal. Like this specific the tag for this image is called the labels. Yeah. And of course, unsupervised learning is just no labels. For example, you just gave all the image to the model and the model learns whatever it can. It could be anything. It depends on the model you use. So a typical example is this. This is an image classification data set. It has like a 60K images and all these 10 different type of images. Yeah, you can see there's dog and the truck and the cars. So if I give all these images and their corresponding labels to the machine learning model, the model can just fit all the images and learn what is all these categories, what is the pattern is. And once it's trained, giving some new data set, new images, the model can do classification for us, like to predict like this is a plane or this is a car, just it. But one thing about supervised learning is its prediction is based on the label we give. Like the previous one, I gave the 10 labels like image, it will just predict dog, plane. But if I just say like these are metal and these are animal, these are metal, like its shape is a metal. This way, the same image, just different labels, the model can only give us prediction either is metal or animal. It doesn't know the specific type image is. So that's why it's called supervised learning. It's like kind of we teach somebody something and it can only learn this kind of thing. These two examples I just showed is called classification. That's because the labels is categorical values. Yeah. But there's also another kind of problem called regression problem. It's like the label is a continuous value. For example, on the Kaggle website, they have a data set to housing prices. It's like for each house, they measure like 79 features, like the location and the size and the like format of the houses. And also, of course, each house, there's a price. And then you can just give all the data to the model. The model can then do prediction for you to predict the final price of each house. So this kind of problem, we call it like a regression problem. So because like, I mean, regression is not a categorical prediction. The actual prediction is a value. So for this kind of problem, usually we compute a mean square error. Basically just compare the prediction price with the actual true price and find out what's the difference between them. Of course, the smaller the difference, the more accurate the model is. And you can see on Kaggle, they actually have this, for each data set, they have a computation. And you can submit your model and check what is the performance of your model. So this one, this group is ranked first. And yeah, actually for the final exam, some students, they don't want to choose project one. They want to choose their own data set. So Kaggle is a very good resource. You can see their examples, download their data set. Actually, the project one, the data set, I just downloaded from Kaggle. Yeah. Yeah, that's supervised learning. Basically, you just need label for all the data. Another type of learning is called unsupervised learning. So yeah, apparently the algorithm are not given any labels at all, and the model just learn it by themselves. And specifically, there are three types: clustering, association study, and dimensionality reduction. So clustering is just this kind of algorithm just group all the samples to different categories based on their similarities. For example, all these 10 images, okay, the model may just divide it into all these different groups. Each group represent a specific type or car or a cat in that. The thing is, the model actually, I mean, let's assuming it just divided into 10 groups, the model doesn't know what each group is. It just tell you like, okay, these images it should be the same, but it could be a shape or it could be a cat. The model doesn't know what it is. It just tell you the other in the one groups. And another type of unsupervised learning is association study. Basically, it's like it's very commonly used in like Amazon or all those websites. They collect all the information, like you buy something and the history, and then they can do suggestion like people like you, if you buy a cell phone, if you buy a headset, maybe you will also like to buy maybe a speaker or something like that. Yeah, it's kind of there's a kind of association between these kind of histories. And and the last one is dimensionality reduction. So this one is like it reduces the number of the features in the data set. For example, this housing price problem, each house has 79 variables. But actually, if you use dimensionality reduction, you can see maybe just the two variables or three variables can give you an accurate prediction. Yeah, I mean, depending on the problem, it is different, but it's quite useful, especially in when sometimes you might have like a million features, you want to reduce it to 10,000 features, and dimensionality reduction is what you want. To summarize, so machine learning just have supervised learning, unsupervised learning, and the only difference is just if label information is provided in there. But of course, like some latest models, actually they can take both labeled and unlabeled data at the same time. So they can learn from unlabeled data, and this process they call it pre-training. It's like you just don't tell what it is. The model just learn first, and then you can give it some labeled data, and this way we have proved that this kind of process can give you better performance. Yeah. So let's see an example. So you are given a data set of emails. Each of them are labeled as spam or not spam. So your task is to build a model to classify them for new emails, like to check if it's a spam or not spam email. What do you think? Is this a classification problem or unsupervised learning? Yeah, that's correct. Yeah, because we need to kind of group them to spam and not spam, and there's a label for the input, so it's a supervised learning. And similarly, and next one, we have a collection of Lego pieces of different size and colors. You want to organize them into different groups so that it's easier to build the set, but you don't know the part number of each piece. Assuming like you don't have the menu, just you want to put them into different boxes so it's easier to assembly the set. What do you think? Is this a supervised learning or unsupervised learning? Right. Yeah, that's right. It's unsupervised learning. Yeah, clustering. Yeah. So it's just put into different groups. Yeah, just based on the size and the look of them. Yeah, that's all about machine learning. And any question about them? So before I show you the script, I see some idea about matrix. So a matrix is just a way to measure how the model performs. And for example, accuracies, we know and also the precision recall, those are just a way to show okay, my model works best. Of course, 100% accurate is a goal we want to achieve. Also, we can use accuracies and matrix to determine if the model is overfitted or something. Oh, by the way, this idea overfitting, it's usually for a data set, we will divide it into several groups like training data, validation data, and the testing data. And this, because a model has some parameters, we want to tune the model, use the best parameter to achieve the best result. But we don't want the model sometimes if you you just let the model learn on a small group of data, the model learns it so well, everything on that data set, it's 100% accurate prediction. But give a new data set, the model doesn't know, the prediction is wrong. This kind of behavior is called overfitting. It's like the model just fit the data you have. It doesn't learn the actual pattern. So we can just usually we use a validation set to tune the model and use a test to check the performance of them. To compute those matrix, you need to understand these 4 terminologies, like true, positive, false, negative things. So this is, I think this is very confusing at the first time. I feel confused because it's this terminology. But the thing is actually so true positive means this thing is positive, and my model predict is as positive too. So it's like a true positive. Yeah, true negative is this thing is negative and predicted as negative, and my model is correct. So that's how. Similarly, like a false positive is just is false prediction. And so based on those 4 terminologies, we have all these different kind of matrix like accuracy, precision, recall, F1 score. It's basically just different ways to show you how the model performs. And so we will show it later in the script. As Python has a classification report function, actually can compute all these things for you at one time. Just one function calculate everything. And also there's an idea called ROC curve. So similarly, there's also an idea called precision recall curve. This is given a prediction. For example, you have 100 samples, you have 100 prediction, but the prediction is not a categorical value, but a numerical value, like a probability, like 80% or 90%. You can then define different threshold. For example, you use 10% as threshold, you can compute a false positive rate and a true positive rate. And then 20% compute another rate, 10%, 30% compute another rate. This way, different threshold, you can get a different point on this figure, and all these points can generate a line, a curve. Similar to that, it's like a different threshold, you can compute a recall and a precision, and another threshold, another threshold. This way, instead of directly give you a performance, you can use this way to check overall how the model performs. Sometimes for example, your prediction is a probability 90% positive, but in real life you don't know if 90% positive is positive or negative. Yeah, sometimes maybe 99 is should be positive. Sometimes maybe if it's larger than 50%, it should be defined as positive. So this way, you can't tell which threshold is better. You can just use this way. As long as I compute every threshold, I can know my model performs overall okay. But this one, it's because this curve is this one is the more it's closer to the upper left corner, that one is the upper right corner. The more accurate the model is. So this area under the curve is a way we use to check the performance of the model. These 2 figures are frequently used in nowadays academic papers, because for papers sometimes we want the paper looks good. A plain table looks too simple, right? We want something colorful, and I think that's very many people, right? They choose using these figures. And also, I mean, these things are for like classification ideas. And for regression, we can use mean square error, mean absolute error to compute the difference of the predicted values. Yeah. So as for which matrix to choose, like, of course, I mean, ideally you should choose the best method based on the topic you want to uh, I mean, you want to achieve. But the thing is nowadays, like even if you choose the best metric, others, the readers, if you still ask like you like, okay, how about the other metric? What's the model's performance on that? So a commonly used way is just I just do compute every matrix for and list all the results there, so that it's more clear, shows that my model works good. Yeah. Um, yeah, that's all about the matrix part. Any questions? In Python, there are many packages for machine learning, expect and also deep learning. But this scikit-learn is the most popular and most user-friendly for beginners because its format is very simple and it has all the classical models like random forest, support vector machine, and it's so simple. Like you don't even know you don't even need to know like what the model is, like what the mathematics is. You can just do prediction, training, and predict in just 2 lines. So we will see how it looks. So let's load the Aries data set first. And so yeah, this is a plot we show like last week. We can see this data set has 3 different type of flowers. And there are 150 there are 150 flowers. Each flower has 4 features of the different lengths of the iris. And so let's to do the test, we first use train test split. This is a function in scikit-learn that split the data to training data and the testing data. So usually in Python, we use X to represent the data and use Y to represent the label. So it's like train data, train label, test data, test labels. And we use a model called Gaussian negative binomial model. So you can see just 3 lines. We first define the model and save it in the variable model, and then use model.fit, training data, training labels, and then model.predict, testing data, and this is the prediction. And that this is all the same for all the models. Like all you need to do is to change this line, maybe to random forest or like to linear model, and all the remaining part is the same. Yeah. And once we do the training and predicting, we can use the accuracy score to compute the accuracies. So similarly, this is like the testing labels and the predicted labels. You can see the accuracy is very high, like 0.9897, because that's the Iris data set. It's a simple data set. This is like a supervised learning. And we can also do unsupervised learning. This using this function called PCA. Have you ever learned PCA? No. Good. PCA is like its full name is called principal component analysis. It's like we believe that in a data set, no matter how many features it has, it should be have some like some principal component, like maybe like I mean, depending on how many compute component you want to compute. Let's say here is n component equals to 2, means I just want to use the most 2 variables that can discriminate this data set. And instead of the whole like a 4, yeah, of course, I mean, in every data set, there's originally it's 4, I just now divide it into two. But for example, for the housing price, we can also do it like even it's 79 features, we can instead of 79, if I just want to use two features to represent the data set, what it should look like. Of course, I mean this this principal components is not the original features. It's like it's like a computed features. It not exist in the previous data set, but we can see actually. I just divide into two components, similarly fit. And oh, by the way, this one, because this is not it's not prediction, right? So it's unsupervised clustering. So we use the transform function. You can see. I mean, this PCA1 and PCA2 is not the original feature, but actually just these two features, it can like clearly separate all three kinds of flowers. So this component is like a computed feature based on the original data set. I didn't I didn't explain the mathematics here. So usually, but you can think of principal component as the component that reflect the variance in that data. So the PCA1 should reflect the most significant variance in that data. Of course, PCA2 is the second most important variance in the data. Yeah, that's how like a PCA means, like intuitively. We can also, I mean, this is just a dimensionality reduction. We can also do clustering. We use a typical function called k-means clustering. And so for this clustering, you need to give it like how many cluster you want. And similarly, you do fit and predict. But because this one, you need to give the actual cluster for each sample. So you will use a predict function. And let's draw this figure again. And now these three samples, all the flowers are divided into three clusters. You can see there are some mixed classification. Like this one, it should be Virginica, but it's actually in another cluster. That's because k-means is just a very simple algorithm. K-means just calculate the similarity of each samples. It just put everything on a space and compare the similarity of every samples and just arrange all the similarity and then put like these 100 samples, their similarity is very small, put them into one group. Those ones, they are very similar, put in another group. So it's a very basic way to compute the similarity, to clustering. So that's why its performance is not so good. And also you need to specify how many clusters you want. If we change it to like 5, yeah, it can still do clustering for us. I mean, even though these two, they should be, these two, they should be different cluster, but they are still grouped into one cluster because k-means thought they should be similar. So let's see another complicated example. So there is a data set how so called means data set. It's a group of handwritten digit. It's basically just a human written digit numbers. Maybe I can show it here. So we can use the load digit function in scikit-learn to load that data set. And you can see each image is just 8x8 image and the pixel image, and there are 1,700 images. We can show how the image look like. So these are just the different handwritten digit, very blurry. It's because they are like enlarged, and you can see this is 0 and 9. Yeah, these are their corresponding labels and how the image look like. So we can change the data to because this is kind of like each image 8 by 8, and then it's kind of a 3-dimensional data, but we want the data set to be like a 2-dimensional. Yeah. So just the sample and feature. So we just put align all the cells, sorry, align all the pixels in one row and then make it into a 64 feature image. And the target is all the labels of that image. We can first, we change it. This is another way for dimensionality reduction, but this one is a non-linear model. ECA is a linear model. It's like a most simple model. We can see we still fit it and transform it and check the scatter plot of the results. You can see even though it's just a 2-dimensional features, we can actually kind of separate all these 9 digits images. And we can also do classification. We split it into train and test. And oh, I forgot to mention this. So this train test split is a randomly train test split, like randomly select maybe 80%, or I didn't set it, but what's the default value? Oh, if train size 9, it should be 0.5. Maybe certain. So yeah, so the percentage is like 75% is training data and 25% is testing data. So it's randomly choose. So this kind of is calculate. I mean this kind of selection is based on the random generator in the computer. So usually, if you change, if you don't set it, it will just use a randomly number. So this time today you run it, you get one result. Tomorrow you can get another result. So if you want to get a fixed result, you need to include this random state. So like give it like a kind of give it a fixed random generated number. This way, no matter when and where you train, I mean, you use this function, the results is always the same. So we split it, and then similarly, we still use that Gaussian negative binomial model, fit the model and do the prediction. And you can see the accuracy is 0.83. That's because, I mean, this model is not a very good model on this classification problem. And we can check using the confusion matrix function to check what is why I got the wrong accuracy. So you can see the confusion matrix is basically based on the true value and the predicted value. It can tell you like, okay, this one is wrongly predict and this one is wrongly predict. Yeah, just using a heat map to show like which results are not correct. And but of course we can, I mean, this can show the wrongly predicted value. We can also label the original image using the script here. And you can see this one is wrongly predicted. So let's see, I don't like the model. I just want to change it to support vector machine. So I just import another model from scikit-learn. And this is actually one way to use support vector machine. So if you search SVM, you can see there are many functions like linear support vector machines, and also SVC. This one is like it can use other kernels and to more complicated support vector machines. So basically, if you want to use it, every function you search its menu, there is an example. All you need to do is to copy this line, and that's it. You can just exchange it and use it in your program. And we define another model and fit on the training and testing data, fit on the training data, predicting on the testing data, and use a classification report to generate all the matrix precision recall F1 score. You can see this one is more accurate. For different images, it's almost 100% accurate. We can also, let's see another example. We can use another model, this logistic regression, to fit on the training data and do the prediction. And because the logistic regression model actually produce the result, prediction results, a probability. So I want to use that probability to draw this RC curve. So because RC curve is only for like a binary prediction, so you can only do this kind of one versus another. So here I just give like this is a Y label I choose for the number one, like what is the prediction? What is the true value for number one? What is a predicted value? And then this RC curve display function can just draw a RC curve for us. You can see the AUC is 0.99. And this one, this dashed line, it means random guess. Random guess is usually just 0.5. So we can see this model also work good on this specific problem. Yeah, that's how. That's basically how we can use scikit-learn like to do machine learning models. In our final exam, there's both two questions requires you to use 3 different type of models to do the prediction. If you are not familiar with them, you can just search the menu and just copy the code from here. Okay, let's see how we can solve this problem. This data set is I have already downloaded from on my computer. It's a little bit weird. It calls CSV, but actually it's separated by semicolon, not comma. So to read the file, we can use specific set using semicolon to separate the data columns. And to make it easier, the question asked to predict the quality. I just convert the quality into a binary label. If it's larger than 1, we say it's larger than 7, we said it's okay, 1. Otherwise, this is not okay, 0. And so then we remove the original column, the quality column, and also change that to a Y as the predicted value. And we can check the data. This is just a data frame, and each row is the information we want, is a feature, and the Y is the labels we use to predict. And assuming I'm a beginner, I don't know how how to use a random forest model. So I can just search random forest. I see a scikit-learn. You can see here, it has the example showing how you can do this. Yeah, it's here. You can just copy it here and then do some. So yeah, we don't need this. This is just the generate a random data set for you to test. So we want to, this is a function used to define the random forest classifier. And we also need a xtrain, xtest. We use a train test split function to divide it into training and testing data. And your test size 0.2 means like 20% of the data is left out for testing. So we then revise this one to xtrain, ytrain, and we can y predict equals to CRF predict x test. And we can also use the y predict probable as the predict probability for this data set. So this is also one special thing about random forest. It's like it can do actual prediction for you, like give you a label. It can also give you a probability. Just depends on how you want for the specific, what kind of value you want. And after this, we can write, and it's done. And I just replaced here. Yeah, gave us the prediction results for this model, all the precision record. And we can also copy that RC curve function to show how the RC curves look like. All we need to do is to change this one. This one is Y test. And this one is Y predict problem. Ah, yeah, that's because, yeah, this is the RC curve. Yeah, I got the error because this predict probable is actually the result is a two-dimensional matrix. We can have a look at it. It's like the first column is the probability of being 0. Second column is a probability of being 1. So I just want the probability of being 1 and use them to predict, I mean, to draw the curve. So I can just do it like this. Yeah. I mean, this is how, like, if you're new, you can learn these things through Google and figure it out. I mean, instead of using ChatGPT. We know ChatGPT is this is actually how I learned machine learning at the very beginning. I know ChatGPT is very easier, but I mean, this way seems stupid. But actually, if you try this way like two or three times, you will remember everything. But for ChatGPT, you can get the answer in like 10 seconds, but you copy it, you forget everything and still don't know what it is next time. So yeah, I I mean, I personally still suggest this way to learn something. In the future, when you get a job, you can definitely use ChatGPT to help you with your daily work. But before that, this is a good way to learn. Yes. Yeah, that's all about today's lecture. Thank you.